Have you ever just stopped and wondered how your computer does it all? Seriously, right now, you might have a browser open, music playing, maybe an antivirus scan running in the background, and notifications are popping up. It really does feel like magic. But it's not magic. It's actually this beautifully choreographed dance. So let's pull back the curtain and meet the master conductor inside your machine, process scheduling. Okay, so how does it pull this off? How can a single processor, or just a few cores, create this amazing illusion of doing 100 things at the exact same time? That is the big question we're going to tackle today. And trust me, by the end of this, you'll look at your computer in a whole new way. All right, to get this, we first need to meet the star of the show, the main character in our story. And it's not the app icon you click on, no, it's something much more alive. It's called a process. Think of it like this, a program. Say, the code for your web browser, just sitting on your hard drive, is totally static. It's just a recipe in a cookbook. It doesn't do anything. But the second you double-click that icon, bam, it becomes a process. It's now the chef in the kitchen, actively cooking, a dynamic, living thing that needs ingredients like memory and CPU time to get its job done. That's right, every single one. That word processor you're using, the game you have minimized, even that tiny little clock in the corner of your screen, each one is at least one active process that your operating system is constantly juggling. So with all these chefs running around the kitchen, how on earth does the operating system keep track of them all? Well, it gives each one an ID card. For every single process, there's a process control block, or PCB. This little data structure holds everything the OS needs to know. Its unique ID, what it's doing right now, how much memory it's using. It's basically the process's entire identity on a tiny digital card. And just like any character, a process has a simple life story. It all starts with creation, the moment you launch the app and its ID card gets printed. Then it has its life, doing its thing, being managed by the OS, and finally, when the job is done, it reaches termination. It finishes up, and its ID card, the PCB, is shredded to free up resources for the next one. But what if our chef could chop vegetables and stir the soup at the exact same time? Now that's efficiency, right? Well, to get that kind of performance, a single process can be broken down into even smaller units of work called threads. People call threads lightweight processes for a good reason. They share the main process's resources, like its memory, which makes them super cheap and fast to create. This is how your word processor can check your spelling in real time while you're still typing. It's how a video game can calculate physics while it's also drawing amazing graphics. They're absolutely crucial for getting the most out of the powerful multi-core processors we all have in our machines today. So every process is on a constant journey, right? It's always changing its status based on what it's doing and what the system can give it. The OS keeps track of this journey through a few different states, and it keeps everyone organized using queues. Okay, so a process can be in one of 5 states. It starts as new, as it's being created. Once it has everything it needs except for the CPU itself, it moves to the ready state. When it finally gets its turn on the processor, it's running. If it needs to wait for something, like a file to load, it enters the waiting state. And finally, when it's all done, it becomes terminated. Just imagine it. You could have dozens, even hundreds of processes all in that ready state, all waving their hands saying, "Pick me, pick me." How does the OS possibly manage that chaos? It's actually pretty simple. It makes them get in line. The operating system uses queues, just like at the grocery store, to keep all the processes organized while they wait for their turn. So we have all these processes, and they're all waiting patiently in queues. But who actually decides who gets to go next? Who's the bouncer at the club door? That's the super important job of the schedulers. Schedulers are really the brains of this whole operation. They're these incredibly smart parts of the OS that look at all the processes waiting in line and make the critical decision of which one gets to use the CPU next. And let me tell you, their decisions are the difference between a computer that feels lightning fast and one that feels slow and clunky. And it's not just one scheduler. There are actually 3 of them, each working on a totally different timescale. The long-term scheduler is like the main gatekeeper. It decides which new jobs to even let into the party. The medium-term one pops in occasionally to manage memory, maybe swapping a process out for a bit. But the real star, the one at the heart of the action, is the short-term scheduler. This thing runs hundreds, even thousands of times a second, picking the very next process to run on the CPU. It's the frantic, high-speed brain making it all happen. Now, for a modern scheduler to be really effective, it needs a superpower. And that superpower is called preemption. This is the awesome ability to forcibly interrupt a running process, yank the CPU away from it, and give it to someone more important. Seriously, without this, your mouse cursor could freeze, just because some background task is chugging along. Preemption is what keeps your system feeling alive and interactive.
So, how do these schedulers make these split-second decisions? They're not just guessing. They follow a very strict set of rules, and these rules are called scheduling algorithms. And this, my friends, is where the real art of the trade-off begins.
So, how do we know if an algorithm is any good? Well, we grade it on a few key things. We want high throughput. That means getting a lot of work done. We want low turnaround time and waiting time, so things are efficient. And maybe most importantly for us, we want a super fast response time, so the system feels snappy. The tricky part is, improving one of these often makes another one worse. It's a constant balancing act.
The most basic algorithm is exactly what it sounds like. First come, first served. It's just a simple line. The good thing? It's super easy to build. The bad thing? Oh, it can be awful for performance. If a really long, heavy process gets in line first, every other quick little task gets stuck waiting behind it. This is literally why your whole computer can sometimes feel like it's stuck on one thing.
So a smarter way to do it is shortest job first. This algorithm always picks the process that it thinks will finish the fastest, and mathematically, this is proven to be the best way to reduce the average waiting time for everybody. But it's got a dark side. A really long but important job, like rendering a video, might never get its turn if a bunch of tiny jobs keep cutting in line. This is a huge problem called starvation. A more practical approach, and one you see in real systems, is priority scheduling. Every process gets a priority number, and the scheduler just picks the one with the highest priority. This is awesome for making sure that urgent stuff, like your mouse moving when you move it, happens right away. But you can probably guess the problem. It can also lead to starvation for all the low-priority tasks. Okay, so to fix this whole starvation problem and make things fair, we have round robin. This algorithm is so clever and so important. Instead of letting one process run until it's done, it gives every single process a tiny slice of CPU time. That's called a quantum. If you're not done by the end of your slice, too bad. You go to the back of the line. This ensures everyone gets a turn, which is what makes your system feel so responsive. So in the real world, an OS like Windows or Linux actually uses a mix of all these ideas. The most advanced strategy is called multi-level queues. They basically create different lines for different types of jobs. You might have a high-priority queue for interactive apps and a lower-priority one for background stuff. And you can even use a different scheduling algorithm for each queue. It's the ultimate in control, letting the OS be both super responsive and super efficient. Okay, that was a lot. We've gone through processes, states, queues, and all these algorithms. So why does this incredibly complex world inside your computer even matter to you? Well, because this entire system is what manages the trade-offs that directly create the experience you have every single day. So after all of that, what's the one single perfect algorithm? The answer is, there isn't one. There's no such thing. Designing a scheduler is all about the art of compromise. It's this constant battle between finishing jobs quickly and making the system feel fast, between raw efficiency and making sure everything is fair. The absolute genius of a modern operating system is that it's performing this complex, dynamic dance, making millions of these little trade-off decisions every single second, all just to create that seamless, magical illusion of doing everything at once.